Start. So we are happy to have Constantin Teleman from UC Berkeley with his condensed thoughts and condensed slides, as far as I can tell you. Okay, Constantin, please.
Thank you for the invitation. Yes, I'm happy to speak about that, although it's very preliminary in terms of definitive results. There aren't so many. There are some simple calculations are well known to experts. So what does condensed mean? The word has come up a lot, I think, both in physics and math recently. So the condensation.
Can you do something with sound, because like it's periodically yeah, some
then my headphones might be broken.
okay.
I could try to just not use headphones. Line. Let's see if that's better.
Okay, can you try?
Okay, that should be without headphones.
Yeah, it's certainly better.
It's an improvement. Okay, good. It means I need new headphones. I guess. All right.
Okay. Sorry.
So the condensation I like to discuss is something that's being used these days in physics a lot, in quantum physics, and also now in topological quantum field theory in connection with symmetries. And it's part of what we call now the calculus of topological defects in quantum field theory. In other words, for topological defects is extended topological operators, and sometimes we call them generalized symmetries. And it's really about making, in the long project of trying to make precise the wish list that physicists tell us they have in quantum field theory, and deciding what kind of math structure we need to execute that. And there are a lot of people I should credit. I'll just put some in the top right, some, do I have a, yeah, I have a pointer, good. Yeah, works. I put some names, so I think that it reached the math mainstream, the notion of condensation, a paper by Davide Gaiotto and Theo Johnson-Fried, and they wanted to use the idea of condensation that would come up in a very crude form to define some kind of higher Karoubi completion of higher categories. So I'm not going to get anywhere near there. I'm going to stay down to earth to topological operators. And this, the thoughts are described by this ongoing discussion, my collaborators, Mike Fried and Dan Fried and Mike Hopkins. And I learned a lot of what's happening with this in physics and symmetries from my colleagues in Simon's collaboration. Okay, so what do we mean by extended topological operators? Well, first we have a QFT which lives in this space, Euclidean space-time, this gray block. And we use two operators in QFT living at points and maybe smearing them by integrating them out over some submanifold, but they start living on points. Whereas extended operators, I've been studying more recently, and their operator of support is necessarily a higher dimensional subspace, often a submanifold, and are not, at least not obviously built from little pieces. In fact, condensation is exactly about the question whether operators like, when and whether operators like this can be built from small localized pieces. Now, topological operators is an easy definition which works most of the time, that you have this ambient quantum field theory, you insert the actual operators like experiments, you blow up something at these red points, and then you have an extended operator supported on this yellow orange line, and you want this to be deformation invariant. So if you deform the line and don't cross any other damage you've done in the space-time, the correlation function you compute should be the same. So the position of this line in this case, or surface, should not affect the calculation as long as you not cross some of the other operators. If you cross them, something will change, and they usually want to try to define a charge to explain how things change when you cross an actual operator.
Konstantin, do you allow supersymmetric quantum field theories?
In principle, yes, but I mean, what I'll discuss will come from a topological theory, so will not be, they will not be seen directly. I mean, because you can have super spaces and so on and fermions in topological field theory, but I mean, I'm agnostic about how it was built from some quantum field theory and Lagrangian. So, but the ambient quantum field theory, yes, certainly could have supersymmetries.
Okay.
All right. So today I'm going to talk about topological condensation, which you could say is the art or science of creating higher dimensional operators from lower dimensional ones. So exactly the question in this case, well, could you have presented this line as like an integral of operators supported at points in some form? An example from physics, which I hope I have right, is if I take ideal magnetic dipoles, kind of know what the magnetic field looks like for those, sort of like this, they live at a point, and you condense them along a line, you're supposed to get an ideal solenoid of finite length if you stop. So of zero width and finite length. So that's an example of condensation. It's not topological because these fields, of course, are not topological in this case. You start from some non-topological operators. And morally for the calculus, what we want to say, I'll try to make this precise, is that the calculus of topological defects should behave like a calculus of embedded TQFTs living in some ambient quantum field theories. And we can partially execute that in that we can use TQFTs to construct and compute at least certain topological defects in quantum field theory. It's a construction which has shown up in many papers in the last year. So one of them by Dan Fried and Greg Moore and myself, we called it a quiche for a reason that maybe will be apparent from a picture. I think it started out as a joke, but Greg Moore liked the term because quiche obviously is a quantum object. So it seemed appropriate. All right. So let's just review very quickly fully local TQFTs and those that we're going to use. So fully local means that TQFTs live on a space-time manifold, and they have to satisfy some cutting and gluing construction under. For example, when you're cutting codimension 1 on a codimension 1, you get a space, and in the borders between codimension 1 manifolds, you're supposed to get an operator and so forth. And fully local means we allow cutting down to points.
By the way, let me ask you an educational question. There is this topological three-dimensional Chern-Simons topological field theory. Is it local? What it assigns?
Yeah, that's going to be example 2 coming up.
Okay, so
but I'm not going to say how. So
you will explain what it assigned to a point, yeah.
So it can be put in this perspective, yes. So and the success of the calculus point out that in order to have such a thing, first of all, such things can be determined completely from the structure associated to a point. It has to be something in a category of an object in a symmetric monoidal category of height or depth equal to the dimension of space-time. And there's a sequence of conditions on that object, which are generalized finite dimensionality of vector spaces and can be stated easily in terms of duals. And the serious theorem is that that's enough to define a TQFT for framed manifolds. And then you can separately bring in topology and study the question of, well, do you really need a framing of a tangent bundle, or is an orientation or spin structure enough? And those can get very tricky, but nevertheless, we know how to address them, the homotopy theory question. Okay, so examples of this that were mentioned have been known for a long time. So if you start with fusion categories, you can build from them the so-called Turai-Biro theories. If you start with braided fusion categories, you can build the Reshetikhin-Turaev-Witten theories. So recently, there's some work on fusion 2 categories by an Oxford team. They're not as mysterious as they sound. They're essentially algebra objects inside fusion categories, so that allows the algebra structure generalizes, allows you to increase the dimension by 1. But as a personal note, that's not as exciting as we hoped, because there's a theorem or a meta-theorem with many versions. I don't know, the original claim may have come from Wen and Kong, that all 4-dimensional TQFTs really are gauge theories, possibly with a higher central extension, Dijkgraaf-Witten class. And there are various versions like that. So in fact, they're not as interesting as one might have hoped to, in this case. And then in general dimension, there are the so-called finite homotopy theories, where the input datum is a space X with finitely many finite homotopy groups, and possibly a higher central extension with values in, let's say, C star, in degree, the cohomology class in degree equal to the dimension of the QFT you want to get. So if you're in dimension 2 and you want to start with X being the classifying space of a group, this would be a C star central extension of a group, and you build a projective gauge theory for that group in dimension 2. Okay, so just to say one word about the examples 1 and 2, to a point you assign the actual fusion category, to the circle one assigns the Drinfeld center and or the co-center, and that's where we get into the issue of spin structures of framings. And surfaces define operations that you can explicitly write, I mean, well, more or less explicitly written by Turaev and Biro, on the boundaries, the centers of phi. Now, for the Reshetikhin Turaev-Witten theory, traditionally starts with what happens. So traditionally starts with the circle and assigns to that a Brady tensor category with a bit of extra structure, a ribbon, a bit more. And with much more difficulty, one can then construct the rest of the theory. It was a substantial theorem. But now we know that you can make up, invent some object X whose center, Drinfeld center, formally is any given Brady tensor category. It will not be obviously represented as any object with internal structure, but all it says is you can adjoin an object X to the three category of fusion categories in a symmetric monoidal way so that it generates Reshetikhin Turaev theory. So
what do you call fusion categories? Sorry, because there are kind of the terminology is certainly not.
Yes. Some people might call this multi-fusion, what I call fusion.
But what is it? Just
well, it's a semi-simple, finite semi-simple category with a tensor structure and internal duals.
That's it. Okay. Yeah.
That's it. Yes. Okay. And it started out, I think, historically because people noticed that you can do a lot of constructions you want in TQFT if you assume that. But I think it's just a theorem which I hope I'm stating correctly. If you start with a three-dimensional TQFT, which is simple in the sense that its center is simple. I did not mean to do that. I just meant to do this. Its center is simple, and which admits topological, non-zero topological boundary conditions. Then, in fact, it must come from a fusion category. So this internal dual that started as a nice thing to have, in fact, is a requirement if you want your theory to have topological boundary conditions.
All right, and so and tensor product, but no braiding, and the second
no braiding
case,
no. The center will have
the braiding. Okay,
the center will have a braiding. Yes.
Okay. Thank you.
So right. So the distinction between 1 and 2 is precisely the ones where this pre-center cannot be described as a fusion category are those which don't have topological boundary conditions, or I think it's fashionable to call them gapped boundary conditions. So. All right, and for 4, I think the construction was suggested long ago, not more than suggested. The construction has two-tier theories, Siegel-style theories, so not fully local, was proposed by Kontsevich. I'll write the formula for the invariant in a second. And after we understood the full locality, I think, in a paper with Frieden, Hopkins, and Lurie, suggested, well, this is how you would construct them as fully local theories in a higher category. And I think that none of us actually went on to write the paper. It's quite old, but Claudia Scheinbauer and her postdoc Tashi Balde are preparing the paper where they're writing out the details. So we know exactly this. They are well defined, exactly in the way we expected them to behave. What we did more or less, we give a recipe along which more or less said, well, if they exist, this is how you have to compute them. There's no other choice. And they're proving that actually, yes, that's a consistent construction. So anything in higher categories, even if it's somehow quote unquote obvious, seems to require lots of work to actually execute. All right, let me just say, don't keep it mysterious what these theories are. The invariant, Kontsevich pointed out, is so if you have a closed top dimensional manifold, you must get a number. And the number is computed from the space of maps from your manifold into X. That's also a space with finitely many finite homotopy groups, if X was so. And it's given by a sum, just counting the maps, but weighting them by their automorphism group, including the higher automorphism group. And when you're counting, if you want, you could add a weight from a Lagrangian. So Lagrangian was a class here. So what to think of is the finite path integral. It's integration over a space of maps, which is now just finitely many points with automorphism and higher automorphism that have to be weighted. And you get a complex number because for each connected component of a map, you can pull back the class to the manifold and integrate it. So M, I guess, had to be orientable if you want to make sense of this integral. So it's an oriented theory. Now, if you want to start defining the object associated lower dimensional manifolds, they're defined by quantization functors, something which assigns a higher algebra to a finite homotopy space. And that can be described either as a limit. So take the flat bundle of unit d minus 1 category, so one shift. Such a bundle can be twisted by a characteristic class that we can compute from the original twisting class. Integration descends at exactly the right dimension to give you a characteristic class of such a bundle. So, for example, a flat bundle of category would require a class in H2 with coefficients in C star. And that's one description, and that's kind of a limit description. And there's a co-limit description, which is a recursive construction where you start making cross products with the homotopy groups of your space, mapping space, not X. And you keep building higher and higher categorical cross products. These are also always finite groups. And the theorem that is required to show this really is well defined is the equality of these two constructions. One as cross product, which are co-limits, and the other as integrals, which are limits over a space. So that's what they need to get things running. And then you can generalize it. It's pretty easy to generalize when you have this to a functor from both these categories to whatever, to the target category, because given manifolds with boundaries and corners, you get a diagram of correspondences between the mapping spaces. And once you know this is a functorial construction, you get your functor. So where does this land? As I said, it's an iterated cross product. So it always lands in algebras in the previous thing you build, the previous thing being algebras and the previous thing you build, and so forth. So it's algebras in algebras in algebras in algebras. Just to avoid a mistake, this is not the same as what topologists call EN or ED algebras, because we're saying that once you have an algebra that lives in a two category of algebras, bimodules, and intertwine, it's a Morita category. And in there, you can define, yes.
No. I mean, but it's not kind of a Hochschild complex like this.
This is some kind of Hochschild complex of the algebra for the manifold. And I think there's a topological chiral homology, or that's what they call it.
Okay.
If this was a sphere, this would be some higher Hochschild homology. These are the increasing spheres. There's the whole. If you have an algebra of that height, you have an increasing sequence of Hochschild homologies. The zeroth one is, if you like, the algebra times its opposite. And the first one is a tensor product of the diagonal over that. And then if this was a higher algebra, you can keep going to have its higher tensor products, and they compute exactly a theory on spheres, the sequence of higher Hochschild homologies.
Okay.
And it stops when you run out of category level and end up with a vector space with a highly commutative multiplication. So examples that are probably familiar, everybody must have seen them at some point. In 3 dimensions, if you start with a space BG, classifying space of a group, the quantization of that ends up being the vector balance on G with a convolution product. That's what the recipe produces. It's a cross product of G with a tensor category of vector spaces. And if you have a twisting class in H3, you can twist the convolution product by that class. In dimension 4, if you start with a second classifying space B2 of an abelian group and the class in H4, the class in H4, by slightly non-trivial theorem in topology, is the same as a quadratic map from A to C star. That's in H4 of B to A with C star coefficient. And that gives a braided tensor structure on the vector bundles on A with convolutions. So without the tau, it's a symmetric tensor category, but with the tau, we can deform that to a braided structure. And the braided tensor category will generate a four-dimensional theory. It's one category level higher than just the tensor category, because the braiding allows you to reuse the algebra structure again. So you have like two algebra structures that commute well enough. All right, so this is the introduction. This is what we're looking at, and what I'll tell you today, I think, I'll tell you two precise things. I believe one is very classical, one I think is newer, and we think we can prove it. And one will be about fusion categories, one about finite homotopy theories. So these are the ingredients. But one question you could ask now, which I won't go too far in addressing, is what's the relation between the space and its quantizations? For example, if you know the quantization, do you know the space? And the answer is negative. The quantum theory has more symmetries than the space X. So not everything about this can be constructed classically from X, from maps of spaces. And also different spaces X can have isomorphic quantization related to that. There are more maps. But there's almost a reconstruction theorem, and getting to it is helped by a notion of condensation. That's what got me a little bit more interested in that we can actually understand this, what this functor does.
When you say quantization, do you mean topological field theory?
Yeah, I mean this topological quantization. So X is the finite homotopy type, and this is the finite homotopy path integral quantization I discussed. What's the connection with actual quantum field theories? It's a connection. The one connection that we know works well is via symmetry. So let me explain that quickly, and then I'll abandon honest QFTs and go back to the purely topological setting. Right, so we'd like to talk about these generalized symmetries of a QFT, let's say a d-dimensional QFT. And well, you can think of a symmetry of something is making it a module over an algebra of something linear. That'd be a reasonable thing to say. So we'd like to emulate that in QFTs. So here I've written the QFT space-time is this blue thing, and it's a bit small, and Z is a QFT living in space-time. And how do you make something act on Z? So actually it requires a bit of thought. So it specializes easily if you make an assumption in a second to something obvious. And the correct point of view seems to be to have, well, first of all, a TQFT in dimension 1 higher, and oh, I forgot to say a generalized topological symmetry, otherwise it wouldn't be a TQFT. Generalized topological symmetry. So you have a TQFT, I called it Q, in dimension 1 higher, d plus 1. It has a quantum field theory at the boundary condition. That's what it means that Q acts as symmetry somehow. And that's the other part. You need a topological boundary condition at the other end. Doing so allows you to what's called dimensionally reduce by just projecting. Think of this as the gray thing as very thin, and just view it as a QFT in one dimension lower. So what we ask is whatever you put on the boundary here, what I call Z tilde, should be such that when reduced, it should give you your original theory Z. So you have to have several ingredients. First, a topological field theory of symmetries, a boundary quantum field theory called Z tilde, and a topological boundary at the other end, so that the collapsing this gives you the original Z. Okay, so let's flesh it out a little bit, right?
But
yes.
Is there kind of a general canonical construction of the boundaries? Suppose that I started with this d plus 1 dimensional TQFT and
Yes.
tried whatever, condensate or whatever, maybe it's a wrong word, want to construct a boundary QFT.
So in general, no. In general, you have to find C and Z tilde so that you get your original thing back. So in a special case, it's a bit easier to say what happens. I'll specialize to that in a second. So the way you want to think about it is, the trouble is that TQFT is not by itself an algebra object somewhere, right? So you can't really ask to make it act on something because of that. So what this does is secretly convert it to an algebra object. The algebra object is the endomorphism theory of the boundary condition C, which if you're lucky could also be a TQFT. And that's the thing which is being made to act on Z. That's really what's happening.
Yeah, the only example which I have classical in mind, it's Chern-Simons and Vezzumino-Witten, but it's already
yes,
quite
Chern-Simons,
complicated.
Vezzumino-Witten, that's a good example, except you don't have a topological boundary in general.
Yeah, so that's what.
That's why you have a topological boundary if you decide I'm going to look just at genus zero operations. Then you do, because then you just need to exploit the braiding, and the object one is a braided as a E2 commutative algebra object inside the braided tensor category, and you can just put that. That works as long as you don't create genus, and that's why in genus zero it looks like the conformal chiral field theories are standalone theories, vertex algebras.
Okay, so then you have this D plus one dimensional TQFT. It produces you.
Yeah.
Actually, it produces you probably the boundary TQFT, yeah, because it's a full TQFT, and you want this boundary to act on the boundary QFT which you were given from the very beginning. Or what's the logic? I somehow missed it.
Well,
you want the action, yeah.
Yes, no, here I would put Chern-Simons in genus zero, and here you can put a topological boundary condition for Chern-Simons. If you just stop to genus zero exists, the obstruction comes from modularity when you go to higher genus.
Yeah, all right. And then I want the action of this boundary TQFT on the Vezzumino-Witten.
Well, to get something interesting to see, you have to start embedding defect lines, for example, inside
Yes.
And then you get topological lines in the theory. And that
okay.
works.
All right. Yeah, I meant full.
Yeah,
okay.
That's right.
Okay.
So the symmetry defines an algebra object acting on Z, and I've drawn two kinds of defects here. One that was completely so what we call defects or topological operators will be the projections of topological defects that are contained inside this sandwich but don't touch the quantum field theory Z tilde. So they just stay inside here or on the left boundary. In fact, the really interesting ones are the ones that touch the boundary somehow. The more interesting ones.
So they are sort of algebra objects. Since they do not touch boundary, you can multiply them somehow.
So well, I can compose them in some way. Depends how large they are. I mean, you have to be a bit careful. And you want to think that central defects come from the center and the higher centers of Q. I'll explain that a little bit. The ones that are here are central in some ways. So the Hochschild cohomology and higher Hochschild cohomologies, whereas those that touch the boundary come from the relative Hochschild cohomology of C relative to Q. Again, you're in a higher categories. This makes sense. So these are I'll give the example of a group. So what are some examples here? It becomes really intuitive if you assume that Q really was an algebra object somewhere. It wasn't just some random thing. And then an algebra object always has a regular module. If you're lucky enough, and these are finite enough to define TQFTs, then you put the algebra object in the regular module, so A as a module over itself. And what does this construction compute? Well, it computes something tautological. If you put the algebra in the center, the regular module on the left, and some other module on the right, you compute the space underlying that module. So in that case, you could say that Z tilde was the same as Z, but with an action of Q. Oh, this should have been Q as a mistake there. This guy is Q. Sorry about that. Oh, let's put Q in the middle. So in that case, and only in that case, you can think that Z tilde is just additional structure on Z, namely the action of an algebra. But in general, if the TQFT are generated by some objects in the category, the boundary conditions are maps from one to that object, and it doesn't make sense to say that the underlying object of Z tilde is Z. You'd like to say that, but there's no underlying quote-unquote thing unless you have some way to get out of the category and produce an honest QFT, and that's what the other boundary condition is for. And that's something not noticed usually if you think that you have an algebra here. You implicitly think, yes, of course, that's what you do. So, but you need it actually in the abstract context. And the example to illustrate the center thing, we can take Q to be gauge theory for a finite, it could be a higher group, acting on a quantum field theory with G symmetry. And C is a gauge fixing boundary theory. It's called a Dirichlet boundary condition. So in the TQFT, you'll be summing over principal bundles over a map to the classifying space. And on this boundary, you're freezing the map to be the base point on this boundary. So that's a standard setup. And the terminology, if I got it right, I mean, it's very confusing. But zero form symmetries, they mean codimension one self defects are embedded in the boundaries, self defects of the boundary. And the typical example is the following. Let's say dimension, the QFT at dimension one, so it's quantum mechanics, the Hilbert space is the Hamiltonian. And having a symmetry means a group of symmetries which leaves a Hamiltonian invariant. And if you can do that, if you have that, then you can, of course, insert at any point you like a group element to act on a Hilbert space. And it doesn't matter where you put it as long as you don't run into other operators that insert it, because we assumed the Hamiltonian was commuting with the group action. So in that sense, that's a topological defect. And you can realize that by using the action of G on the Hilbert space. So in this case, it's an algebra, so Q is now the group ring. I could even write that for real. So Q is now the group ring. The space itself becomes a modular over the group ring, and on the left you can put the Dirichlet boundary, the gauge fixing boundary condition, or the group ring as a modular over itself. And here you can see how you place topological defects away from the actual quantum field theory, because here what do you have? You have looking at G bundles on this in the interior of this sandwich. But here they have to be trivialized on this part of the boundary. Here they have to be trivialized, but now you're free to choose how you match those trivialization at defect point. And that's a defect point which projects to your internal defect in the QFT, and the fact that here you can move it wherever you want expresses the fact that here you can move it wherever you want. Whereas if you had defects that were to touch the QFT on this side, there would be no reason to believe that they're topological defects, that they can be moved freely because this side is not a topological theory. So that's how we take out the topological defects out of the quantum field theory and reduce to calculus defects. Now, I'm not claiming, and I think it's an open question, whether any topological defect that you find in the quantum field theory can be implemented by this construction. I think it'd be very nice if that was true, but maybe that's optimistic. I'm not sure. But this construction does allow you to implement topological defects into the calculus. All right, and the final observation in the center is the difference between operators that are frozen on the boundary and those that are inside. Those inside are central, and there are fewer central operators than more general operators. And you see that by noting that you can push them to the boundary. In fact, if you push them very close and go very far away, you can't tell they're not on the boundary. But something that's frozen on the boundary cannot be moved inside if it wasn't central. So for example, in the case of gauge theory, here you could have put any element in the group algebra, but a defect inside here, well, a classical defect would just be a ramification point for the bundle, and you'd be determined by a conjugacy class in G. So here you could put class functions on G internally as defects, but something as no conjugation invariant could not come from a class function, so you wouldn't be able to move it inside freely. All right, and that's the connection now, the connection of Hochschild cohomologies. How do we do calculus with defects? Well, you have to decide what you want from them. And what do we want from a defect? We want to say we've put something here which changed the theory. And let's say we're in top dimension. What do we like to say then? Well, one way to do it is to isolate the defect and take it out of your space-time because you knew what you had. So excise a tiny tube around the defect. And then you're left with a boundary, a sphere bundle of the defect. And now to explain what happens in the field theory, you just have to insert a state on that sphere bundle. So at The base level, you say a defect, would simply be a state on the sphere bundle, total space of a sphere bundle of that defect. But we'd like to do a calculus here somewhat local. I mean, the interest comes from defects that are built locally, just like as if it was an embedded quantum field theory living on D, supported on D. That's the kind of thing. So you want to specify some local data which would integrate out, quote unquote, it's a TQFT style integration to the defect.
But should I think morally? I mean, morally, this modification by kind of a Hecke operator corresponding to this defect, and you want to have sort of a local formula, sort of
well, a Hecke operator, if you think of it as a point, then it's already
not
local.
necessarily. No,
if you
no, no.
if you're on a complex surface, for example, and do some transformation on a curve inside, then that's right. You would like some local way to do that. And yeah. I'd be surprised if you could do it in that case, because you have to be able to cut up the surface into pieces. I'm not sure that. Yeah, in the algebraic geometry setting, I think there are people working on number theory.
No, morally,
but
only morally.
Yeah, morally, that's what we want to do. Yeah, to make it local.
Okay. Mm-hmm.
All right. So here's how we do it. Well, so look at the linking sphere over just a single point, and if you take the original theory Q and evaluate on that sphere, reduce it on that sphere, you get a theory, a TQFT in dimension. Did I write a dimension? Maybe I didn't write a dimension, but it's going to be. I wrote the codimensions here, but yes, the linking sphere has dimension L. So drop the dimension of a TQFT by L. And now what you're looking for is something which inserted locally there could integrate out to a boundary state. And that's simply what we call a boundary condition for this TQFT. So the defect datum you'd like to supply is simply a boundary condition for this Q of SL, and what it is algebraically, so it's not talking vaguely. Oops. This is an object in amorphism from 1 in whatever world you are living up to Q of SL, in whatever category level you are living, which I lost track of. It's got to be a D plus 1 minus L minus 2 category. So it's inside the D plus 1 minus L category, which is in the I think L-fold loop space of the original category where the TQFT lives. Original category. It's something very precise. And then there are finiteness conditions on this, so it really defines a boundary condition. But that's what you're looking for. And for example, if Q is built from a pi finite space, you're simply going to have to quantize the mapping space from the L sphere to X. And that will have a constant copy of X, and then a copy of the L-fold loop space of X. There's possibility of some twisting depending on whether X is simply connected or not. And that's a D minus L algebra built by cross products from the homotopy groups of this space. So boundary theory for that would be a module for this higher algebra iterated cross product. Some people call it a D minus L representation of the groupoid. And you can get such examples topologically from maps. The second Y is an X, I'm afraid. Don't know why it became Y. By quantizing, by letting, well, by quantizing the homotopy fiber of the map. If you have a map like this, the loop space of X, which is a group, acts on the homotopy fiber of the map. And that's the representation you're building. So there's a topological construction of lots of boundary conditions. Now, I'm going to skip some complications because they're not relevant for today. Because if a normal bundle is not trivial, you have to worry. If the tangent bundle is not trivial, you have to worry about what kind of structure you need to define these TQFTs. And that itself can be open a can of worms. Yeah? And even if you start with these finite homotopy theories, if the space X has lots of k invariants, lots of homotopy groups, and lots of extension classes, k invariants, you'll find that you may not be able to get away with just orientations. You might need more tangential structure. All right. So these are the defects we'll talk about, and this is how they fit into symmetries, I hope. And maybe that's a good moment to pause, because now I'm going to get to condensation. Are there any questions?
So have sort of is it kind of a theoretical device, so you can really construct higher dimensional examples of this?
So there is, I think there are two God-given examples of higher categories of arbitrary level. One of them is a Bordy's category of manifolds up to a dimension, right? And the other one is algebras in the Morita category of algebras, the Morita category of algebras, blah, 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 as many times as you like. That's already a little tricky to construct because you have to have co-limits so you can define tensor products. But there's a paper that does it pretty carefully. I think Claudia Scheinbauer and Theo Johnson-Fried wrote some years ago. And the unpleasant thing in both cases, even though these are the two God-given examples, it's actually very hard, very hard to fit them into the preferred definitions of higher categories. They just don't match. So the definition that's good for theoretical work on higher categories is very bad for showing that a natural example is really an example. Just that's the state of the subject as far as I understand now.
Yeah, but it's in general, it goes back to Siegel axioms of conformal field theory. Axioms
yes,
nice,
but he didn't get very far into categories, so there we don't have a problem yet.
Yeah,
I think we're going to be. It gets difficult when you get once you get past two. Actually, with two, I think we're pretty good still. I think it's you don't. I mean, it's not possible to write good combinatorial models anymore because you can't write good simple combinatorial models for homotopy types, and you need to allow that in because you don't want to say that everything is strict because then almost nothing would be an example. So we're just doing that.
Okay.
So that's a difficulty, and that's why almost any theorem that proves that some construction really gives a valid TQFT tends to be long. So, but it's reconciling a theoretical definition with the example usually. All right, so let's get back to condensation. So what do physicists want from condensation? Well, they want to say the following. We'll start, let's say, point defects, but you can imagine there's another manifold going across normal to the board, so it could be any dimension. And if you put lots of points very, very close together, they say you zoom out, it looks like a line, so here you increase the dimension. You got a defect of one dimension higher. That's one thing they want to be able to do. Now, what do they want from? What properties do they want? Why do they want that? Well, the property at least it's supposed to have is reduction to codimension 1, which is if a defect has been condensed this way, and it's supported on, say, a K-manifold, then you can actually forcibly make it supported in a smaller subspace. I'll return to that more precisely in a second. If it was condensed 2 layers, twofold, then you can reduce the dimension of its support by 1 dimension again. And here they would say, well, let's zoom back in and see all these gaps, tell you it's actually a 0-dimensional thing. Now, let's do a math insertion here because this does relate to something that's mathematically precise. If you have a, that was a D, I think, this illegible letter here. If you have a D-connected space and the manifold M, and you're looking at the space of based maps from M to X, you can arrange for them to be supported in codimension D. So the more highly connected the space is, the more you can constrain the maps on the manifold. It's a version of Poincaré duality. So that, I think, for us was a connection, interesting connection, because clearly this condensation thing is asserting some kind of connectivity, clearly, because of this restriction to codimension property. Now let's make this restriction to a smaller thing more precise. Let's call it the ripping open theorem. Let's say you have a condensed defect on a surface, you can rip it open, punch a hole in it, and you can glue it back together if you want. And so in particular, it tells you that the defects are endable. They can have an end. They don't have to be supported on closed manifolds. It's a condition. And second, they do not detect topological charges of operator via braiding. So here I draw the surface here. Let's imagine we're in 3D and there was some interesting QFT operator inside, topological or not. Then Okay, it's a big topological difference on this side if the point is inside or outside. You have a Gauss law, for example, detecting a charge of the operator through the surface. Well, if the operator this operator was condensed from something lower dimensional, you could rip it open, then you could pull out whatever was inside, whatever charge was inside, and then close it back again and move the charge from inside to outside, so there can't be a charge, meaning they cannot detect charge in the complementary dimension anymore. So, all right. So now if you look at this endable thing and ripping open and putting it back together, clearly what it wants to say is that you have a very small interval with two endpoints, which before, because you weren't looking at very carefully, looked like just a dot. And if you have two of those, you can somehow magically put them together into a longer interval. So you have lots of those, you can put them together. And the magic is not actually shocking. We know how to construct a map between those two guys. There's an obvious bordis that does just this, which can be read in both ways. So it gives a bordis this way or a bordis back. So there are maps between these two, relating these two pictures. But in general, they're not isomorphous. They're not, if you compose them, you don't get a trivial identity maps back. So something is required to say that actually you can, in fact, produce this from that. And the something is there's some algebraic operation involving the ends somehow, which allows you to produce the same effect as if you had the interval. And that does the job of the ripping open theorem in a way, because the algebraic operation you're doing, the calculation, does not happen in space-time. It happens on your sheet of paper, so it doesn't interfere with moving a point across. So that would do the job. So that's what's attempted to be done. All right, I wonder if I should put maybe the statement, which I think we can prove here before I define condensation precisely, because that gets somewhat technical. So we thought about one-fold condensation, we think we understand, and that seems to be enough to do what we want for a topological space. Okay, let's start with the topological theory defined from a space X, and in general by Qm of Y for a space Y. I mean the quantization as an algebra in the M category I told you about. And now I'm going to look at defects of various codimensions in the theory generated by X specifically. And the defects will come in two rows. The first row I call them Wilson defects, the second I call Tooth defects, because if you're in dimension 3 and you're looking at lines, so if n is 3 and looking at lines, the top row indeed can ignore pi naught, basically. Is pi 1 of classifies is related to Wilson defects, and pi 1 also is related to Tooth defects, but in slightly different ways. It's representations of pi 1 that labels Wilson defects, and points in pi 1, if it's abelian, label the Tooth defects. The Tooth defects are singularities of the bundle given by the monodromy around the loop, whereas the Wilson lines are representations, and they're changed the partition function by inserting the trace of the monodromy of the representation around the loop. So that's why I'm calling them, I'm extending the name to everything. All right. So here I'm listing in every dimension what defects you have, where they come from. They arise by quantization of the mapping space with a linking sphere. And here are the homotopy groups. I think I've secretly assumed that pi 1 doesn't do any damage, doesn't act to do any damage on the others. And in red, the red squares tell you which defects are new, in other words, which are not condensed from the previous stage. So we'll notice something, that if we look at defects of various codimensions, and you, let's say you mod out, I'm not quite sure what that means rigorously, but let's say you set aside the defects that you already knew by condensation, at every stage you seem to get the homotopy groups of X, which would suggest that yes, the TQFT actually captures the information of the space X, because you can see the homotopy groups there. Have to think about extension data, but let's set that aside. But this is not exactly right, because if you look at the entire diagram, you see that every homotopy group appears twice. At the last stage, in fact, it's completely doubled. The last stage, the link is the zero sphere, which are 2 points. So you really have X cross X you're quantizing. So the secret behind this doubling is something called electromagnetic duality of quantum field theories. That's something which cannot be done on spaces. And that tells you as a move which can flip upper homotopy groups down below without changing the quantum theory. So in a sense, upper half homotopy groups are redundant when building a TQFT. It's enough to look at spaces which have homotopy groups only up to half a dimension. And if you do that, then the doubling problem disappears and you recover the homotopy group somehow. It's a preferred space which generates a QFT which only has homotopy groups up to half the dimension of the theory. So that you can detect by condensation. So I found that an interesting topology application, because without that, I mean, from this slightly strange higher categorical object, extracting the homotopy groups of original X doesn't seem like an easy task, but it's clear the information is there. Okay, and now let me tell you what's involved in one-fold condensation of the example, which has been known for a long time. So this has been studied, of course, in low dimensions in physics. Kitaev had some notes he shared with us some time ago from the braided case. We're trying to write it up for finite homotopy types in general. We understand from homotopy theory. And we identify, I think, 2 ingredients that are needed to make this move work. The move here of somehow merging 2 ends to get an interval and the higher dimensional analog. And one is a notion of Dirichlet boundary condition of a TQFT and generalized to embedded defects. And that's like a generating module for the category of modules over an algebra. But it has to be said in a higher categorical set. And the second ingredient that comes in is a correspondence between internal algebra objects in a tensor higher category, possibly, and module categories for it. And that's the theorem of Ostrich in the case of fusion categories. And full generality, I think you have to impose conditions to get an actual correspondence. So the correspondence is easy to state. If you have an internal algebra object, you have a category of internal modules for it, which is the module category for the ambient category. And going back, if you have a module category, and I should have added here with a generator, oops, plus a generator, preferred generator. You can define an internal endomorphism object of that generator, which is an algebra object in the category, and then you can cross your fingers and hope that actually is an equivalence there. And for fusion categories, there is actually. And I think I've been told recently that people were able to write it up for fusion 2 categories as well, so 1 dimension higher. So clearly, it's our meta statements that must be true if you find the right hypothesis, which we do. All right, so I don't think I'll have time to go over the details, but let me just give you an example in 3 dimensions. Oops. So in 3 dimensions, we start with a fusion category F, which gives a 3-dimensional theory. And the theorem known, probably may have been known in physics before math, that all condensed line operators are scalars. There are no interesting condensed line operators, except a silly thing. You can draw a line and say, well, the effect of this line is to multiply everything by a scalar at the level of the computing partition function operators. On the other hand, there are no new surface operators. All surface operators are condensed from lines.
So I'm confused, sorry, about one.
Yes.
Probably I misunderstood, but the usual Wilson line operators in Chern-Simons, they are not examples.
They're not condensed. They're not condensed from
topological. Yeah. Okay.
You can't even end them internally. You can end them on a boundary, but not internally.
Yeah. I cannot condense. Okay.
That's a problem. So that's right. So actually, in TQFT, there wouldn't be anything to condense them from, because if it's a indecomposable fusion category, the only point operators are scalars. They condense to scalars, so they don't do anything. All right, now surface operators are codimension 1 things. They are FF bimodule categories, and the little theorem is that they correspond to module categories for the center, because these 2 guys are Morita equivalent as fusion categories. And then by Ostrich's theorem, they correspond to algebra objects in the center. And here's a picture that gives the correspondence. Inside the center, you can have an algebra object, and is defined up to Morita equivalence a priori, but fixing the end of the condensate pins the actual algebra object. So here the codimensional surface operator is this orange surface you see, which is a FF bimodule. And that gives a module over Z of F that contains a Morita class. But part of the datum you have to specify is how you end the condensate. That's an end of the condensate. And that will fix the actual algebra object instead of the Morita class. So that's how surface operators correspond to algebra object in Z of F. And these are points in Z of F. This give you label for line operators. So this A give a label for line operators. So once you surround the tiny interval with the circle, you get, or you make these horizontal lines very, very short, that becomes a line operator. But the theorem, which I'm not proving as a calculation, is that this surface operators does have Dirichlet boundary conditions. So let's try to write that precisely. Did I define Dirichlet? Yeah, this diagram isn't so. Let's keep this diagram. Maybe I didn't write the definition of a Dirichlet condition. I don't want to go over a big diagram. You have the slides in time. So maybe I'll write a line at the end here. So let's, for modules, you would say that M is a Dirichlet condition for an algebra for A if it defines a Morita equivalence. You can write with endomorphism over A of M. Well, the better way to do it is define a dual M check and do the usual thing that M tensor over A with the other way around. Sorry. M check tensor over A with M should be equivalent, become Morita equivalent to A by M, the pair M and M check. It's tempting to try to weaken that by saying it's just a generating object of the category, but that condition I don't know can be generalized to higher categories, because generating object, that's a weaker notion. Generating module would mean that generating object for a category mean that the functor generating, say, object in the category G, so the functor that sends an object X to home from G to X is faithful. But faithful doesn't generalize to higher categories well, because injective doesn't mean anything once in higher categories. So all I can say is an equivalence. That's if you like, maybe it seems to be a problem with the general setup of the theory. But once you say that, that kind of forces the original object to be equivalent to an algebra. So in other words, you can only talk about Dirichlet conditions for things generated from algebra. So that restricts a bit. That's what this slide was supposed to show. I'm skipping the world of categories in which you can make sense of this. So this is something that's still a bit open. What's a good setting in which we can find Dirichlet boundary condition, generating boundary condition in this sense that is not just algebras in something, algebras in algebras. There's a more general setting than that. That we don't know. So, but this works, of course, the case of algebras and fusion categories. We can work on that. I think I'm already over time, so I'll stop here.
Well, first, you are not over time, but thank you very, very much. Yeah. All right. Are there any questions? Actually, in this example, which kind of I cannot forget, this Chern-Simons and
the Chern-Simons, yeah.
And Vezuminovitin, yeah. So what are what are these symmetries of Vesumin? Are there any non-trivial symmetries of Vesumin?
Well, yes, because the line topological line operators from Chern-Simons can be, if you like, you can push them on the boundary of the conformal field theory, and they're perfectly well defined. You usually cannot end them on the boundary unless there's got to be some special. Okay. No, you can end them in vertex operators, I think, maybe.
Yeah. I thought that.
Yeah. You can end them in vertex
operators.
operators, non-topological. Yeah. But there's a funny story there. I don't want to take up too much time, but let's think of it. So let's say this is a tube in WZW for a group G. Then you can put a defect, generally non-topological defect, by making a cut here and putting a map from this interval to the group, where you just say that here you make a jump by the group. By a given group element. So this is the path starting at 1 and ending at 1 in the group. And then not a topological defect. If you compute, say, the trace, to close the compute the trace and start moving this around, of course, then the answer changes. The trace of this operator acting on a Hilbert space, which is highly non-trivial. But now, if you put a whole circle around the circle is constant, a constant map to the group, then that's a topological that you can slide about as long as you don't cross other operators, and you won't change the propagation. But then you can ask, is this endable in any way? And I think the answer is not endable, and it's one of the Verlinde conjugacy classes. And then you can end it in the vertex operator. So but here we're pushing the envelope because this is the topological operator, but we're asking about, is it condensed in a condensable from non-topological things? And then the answer changes. Oh yes, here's an example of condensation, if you like, WZW. Here's my claim. I don't know how easy it is to make precise, but the claim is that full WZW condenses to Chern-Simons.
Yeah, it would be great if you can make it precise.
So, because the picture we like to draw is exactly this picture, right? You put Chern-Simons in the bulk and WZW end, and now we just do a contraction of these ends. So this one was be green here, and you get a bigger Chern-Simon. So by the time you contract it completely, you just get Chern-Simons. All right. So it's there should be an example of condensation, but not topological, definitely. But of course, I think we're still playing around with topological theories because there's a lot of applications and there are things we haven't sorted out. But I think you're completely right in your question that the interesting thing is to get this to really apply to honest quantum field theories.
And actually, Gayota, of course, had plenty of examples of boundary theories, of not necessarily topological theories, and which are boundary theories are not necessarily topological, maybe partially holomorphic, like this Castello stuff. So and also there are some degeneration of quantum field theories themselves. So kind of very, very long ago, I wrote even a paper about this collapse, like Gromov-Hausdorff collapse for quantum field theories. And I'm wondering what happened with symmetries, with topological symmetries, when you collapse your boundary QFT. So plenty of questions, really. Yeah, it's very interesting, really. Okay, more questions? So let's give 10 more seconds for people to think. It's all new, maybe that's why they're quiet. All right, then, well, thank you very much. Very interesting and inspiring talk, Constantin.
Yes, thank you very much.